here, I really want with this talk to focus on the market aspects. Henrik already mentioned through his recommendations some stuff that relate to markets, but here I would like to focus on the machinery somehow, how we can actually harness the flexibility in the market-based framework and also reward the agent for this flexibility. There's a lot of people that have been involved in this work package and related activities. I think in terms of scientific output, the work package brought 30 to 40 scientific papers, maybe. 3 PhD students graduated within the work package, and there's been a lot of international collaborations. So obviously within 15, 20 minutes, it's difficult to cover everything. There's 2 aspects I want to discuss. The first one, which is one of the starting point for this work package in cities, is to have a top-down view and say we have different energy systems, let's say electricity, gas, and heat, and we want to find some market-based approach to coordinate those, right? So that's kind of high-level perspective and a top-down approach. But then there's been really an increasing momentum over the last 4 or 5 years towards these energy communities and peer-to-peer exchange of energy, not physically, obviously. But still, it's something that has been very big within cities also, and in terms of work at DTU and with collaboration. So I also want to cover this aspect. Right, but first of all, the markets for integrated energy systems. One of the things that we know for some time, I think many people around the world have been working on these topics. We had lots of interactions with colleagues in China, for instance, and in the US. When we look at these integrated energy systems, our first strategy, let's say, as engineers who love math, computer science, and optimization, is to try to make a big model for all these systems together. Already, when you want to do that, you find many challenges. There's going to be non-linearities, there's going to be non-convexities. There are aspects with the gas and heat systems that are quite more difficult than what we're used to with electricity. But actually, that's also that bring the storage and the flexibility in these systems. It's those non-linearities and the kind of storage you can have in the pipelines, for instance. So let's say we want to do that. We could do it. I mean, big computers, good math models, we can do that. But something we realized through cities and also during different works is that actually this is not something that's going to work in practice, this complete coupling that I mentioned here, because there's some reality of separation of the energy systems. It might be due to operational practice, it might be due to politics, it might be due to many reasons. But we have the example in Denmark, the electricity and heat systems are managed separately. And it makes sense, but that also means that we have some funny ways to interface them as of now. And that's our role, to try to think how we could rethink these 2 systems together in a market environment. So we have introduced something that we coined loose coupling that we looked at for electricity and heat and also for electricity and gas. And the idea of this loose coupling is that we try to find some optimization-based approach for this market so that we get the most out of these systems together, but also respecting either a temporal sequence or an operational practice or some limitations in the communications between agents, so that it's something that could be readily applicable in different areas of Europe, for instance, with different operational practice and political views on energy system interaction. And we had a few examples through the work in cities on how this could work out. So I give you an example here, which is for Warmelast. We interacted quite a lot with HO4 to look at what is the sequence for decision-making in Warmelast and how it links to electricity market. And what's very important, we don't need to look at each and every block, but what's really important is that it's going back and forth, right? The heat system is thinking first, you could say, and then the electricity system reacts to that, but still it's going back and forth between also the heat market, even though it may not be a market in the same sense as for the electricity system, it's more of a cost minimization approach. And there is this interaction. And then the producers, so think of CHP operators, they are the interface between heat and electricity, and they are somehow implementing the coupling. So we looked at different ways how we could respect this idea for the sequence, this interfacing between the CHPs in between the heat and electricity side. And most importantly, what happens eventually is that you have some kind of leader-follower structure that is known by those who do some hierarchical optimization, where you would have somehow the district heating, think of it as the market or the system that makes decision first, but it has somehow to think of what would happen for the electric power system in the second stage, right? So if we respect this sequence, what we looked at is how we can write these hierarchical optimization problems so that we can have a heat system that has a market that comes first, but that acknowledge the fact that there will be the electricity market in the second stage with its ancillary services, etc. So somehow when we clear the heat market, we try to optimally position all the units that are at the interface between the heat and the electricity market so that they also bring optimal social welfare in the electricity system through energy and ancillary service provision. So it gets a bit heavy mathematically, but still, and computationally, but still we found some ways somehow to implement it, and we made a few, I would say, demonstration based on case studies that this could work out. On the other side, we have the electricity and gas system together, and there are many different situations around the world. In certain countries, the system operator is for electricity and gas. So for instance, in Denmark, Energinet manages both the electricity and gas system. It also happens in the UK, but for instance, it doesn't happen in most other European countries. So we have to find a way to coordinate this system that is agnostic to the fact that maybe the system operators are kind of the same or together or not. There's also different aspects to look at is how we're going to consider this, this coupling. There's most likely two stages for decision making for this market. There's a forward stage at the head, and then there's the near real-time stage, which we call balancing for electricity. And maybe in other places, we just call it real time. So you have it here on the left here, on the y-axis, you have DA for day ahead and RT for real time, okay? And then you have the big letter E and the big letter G, which it comes for electricity and gas. So then you see these four blocks here. It's four different types of options we've been looking at for coupling or coordination of these systems. So here on the left, it's fully decoupled in time and cross sectors. Then we've been looking at coupling in time. So how we may have some stochastic optimization. So we make decision in the day ahead, trying to think of what could happen in the real time, but we don't couple electricity and gas systems. They just run their life somehow in parallel. And then we've been looking at coupling cross sectors, but not in time. And finally, we've looked at the full coupling, where you have a coupling in time, so stochastic optimization for trying to make decision in the first stage, looking at what could happen in real time, but also a full coupling of the sectors. Somehow we've been exploring the different views on how this could work out, right? Another aspect that's very important, I mentioned for the electricity side, for the electricity and heat side, sorry, is that here I just show you some coupling, which is by design. But eventually in practice, the coupling can come from different agents that are the interface between the different systems. So here we also did a lot of work, which is actually not published yet, it's under review, where we look at these agents that would be there to help with this coupling. And these agents could be virtual bidders, which is something that is vastly considered, for instance, in the US. Or these agents could be self-schedulers. So they are agents that are out of the market because somehow it's believed with the information they have and the way they behave, they could do better if we allow them to self-schedule than if they are scheduled through the market. So you could say it's a bit counterintuitive. We have a market for coordinating, but actually there are some agents that we allow to be out of the market because we believe it's going to help. But this is a reality, and it happens, for instance, in California. All right, so very quick, I'm not going to have many results here. It's mainly a point of discussion of all the work we've been doing. But something important with electricity and gas is that it's quite difficult to model the dynamics in the gas system, but you need to account for these dynamics if you want to reveal the flexibility on the gas side and accommodate it and reward it eventually. So a lot of work has to be put into this modeling trick and the computational aspects if you want that to be there. Then in practice, we've been looking at very simple ways to implement this coordination. For considering the 4 quadrants I showed you before, we've been looking at also hierarchical optimization, where somehow we would play at upsetting the merit order in the day-ahead market so that the units that are the interface and that can provide some flexibility get optimally placed somehow in the merit order so that they are in the market, you could say, but still they have room enough so that they can provide flexibility at the balancing stage. So you can do that through prices by distributing some kind of premium, positive and negative, to the different agents in the day-ahead market. And we do that with some fairness constraints to be sure that in the long run, we're not affecting the positioning of the different agents in the market. There's also some way to do it with a volume-based approach, where you will consider controlling in a way. It's not really control, but you're going to try to impose some volumes of gas available for the different units at the day ahead and at the balancing stage, so that they also are affected in terms of where they are in the merit order. And it actually have a huge impact on what we get out of a market, combining the day ahead and the balancing stage. All right, so now I want to move to the second topic. It's energy communities and peer-to-peer markets. There's been a lot done at DTU and in other universities, and even also by various commercial and industrial partners throughout the world. And I just want to give an overview of why we care about it and what could be done with that. So we all know the system is getting more decentralized, but in a way, the same way we want to try to see if we can adapt markets to the interaction of multi-energy system, integrated energy system, we should also try to see how markets could accommodate this new approach to decentralization of the energy systems. We have considered a lot aggregators, and it's a great idea, but there are other approaches that are more bottom-up, where we would allow all the small agents, prosumers and others, to aggregate by themselves, all right? And that's what people call energy communities. These energy communities or peer-to-peer setup come in many flavors. Here, I just copy-paste with authorization some plots by Para and Sovakul. We can consider it as a full peer-to-peer network where everybody can just trade with everybody. And we've been proving mathematically that it is just a generalization of what we do today. So it's not a completely new system, it's actually just a generalization. We can consider isolated microgrids, and I think quite a lot of experiments that have been there with peer-to-peer are actually based on the idea of microgrids. Some people have considered interacting microgrids. So we've all heard of some kind of cell projects in the past, right? Where these cells could disconnect and reconnect to the grid. That's what it is, and it's the scheme V here. And the final one on the right, the D, it's this idea of virtual energy communities that we've seen discussed in many works in practice or in the scientific literature. And that's maybe what would fit more a society like Denmark or Western societies, where people would want to just gather and decide they have some common interest in terms of energy. All right, and something that is very important, Henrik was mentioning labs and trying in practice. It's also one of the topics where it's very important to go all the way from the theoretical aspects in mass and regulation to the very practical aspects. So there's been demonstrations done in Denmark and in many places around the world. We've been interacting with people as far as Australia for this kind of demonstration. There's one living lab, you could say, which is Svalin, a Bofellescab in Trekroner in Roskilde, where there's all the work that has been done has been implemented. There's been some work in Nordhorn, where there is very interesting. The peer-to-peer and energy communities are for heat and electricity together, or the idea is more to see how we do the same as we did for electricity for heat, and eventually we make it for heat and electricity together. But I wouldn't want to be unfair. I mean, these are only 2 examples, and there are many other initiatives in Denmark and other countries. And I know, for instance, I've been discussing with Norlys, where they also have some initiative in Ireland. So that would be some kind of, look at it as system/market operator here at the top. But the idea of the organization of the system with this kind of energy communities, it would be quite similar to what we think of if we have aggregators. except that here, the main difference, an aggregator would be a for-profit agent, and these energy communities most likely are not for-profit agents, right? So in the way, anytime they're gonna generate benefits by interacting with the overall system, so it can be the energy market or ancillary service market, all the kind of benefits that would come from this participation will be directly redistributed to the community members. So that's one of the main difference. After, in terms of how it's going to work with control, mathematics, market participation strategies, there's a lot of similarities. Just one example, which is very simplistic, but just to give a feel for why it is interesting. Normally, when agents participate in the electricity market, the small agents, they are buffered, right? There's a retailer, or some have talked about aggregators that pool everybody. But that means somehow that all the agents at the lowest level are passive. They are not really acting themselves in the market. Well, if we go for this peer-to-peer or energy community approach, actually the agents to the lowest level will actively participate in the system, maybe through some Raspberry Pi or some IT within their house or their asset, but still they're actively participating. So they can reveal their preferences. And for instance, some kind of preferences that could be revealed is to buy energy as locally as possible. This cannot be a hard constraint. Obviously, if there's no production of energy within your neighborhood, you're not going to buy from your neighborhood. But here we've made a small example, for instance, which is part of a published paper, where we looked at how we can use this peer-to-peer market to also account for the preferences of the agents to buy energy locally. And with this small parameter you see on the right, so C and G, is this parameter to tweak how important it is for the agent to buy energy locally. You can see the outcomes on the left. So there are 3 lines. With first line, agents don't care about buying locally. Second line, agents care a little bit. And third line, agents care a lot. And in terms of the market outcome, which is the first column here on the left, these are the trades that can come out of the peer-to-peer market. You can see in the first case, when the agents don't care so much, the trades are all over the place between these 2 villages, you could say. In the second line, there's less trade between the 2 sides. And in the third line, the agents only buy or exchange energy locally. And this is something, if you look at it in terms of a bottom-up approach and what would happen for the whole system, so you go from the micro to the macro, somehow when all these agents are expressing their preferences, the outcome of the overall electricity market would look very different. So people may think that this idea of energy communities is just peanuts, you know, people just want to do their thing, let them do it, but we control them locally. Actually, if we were to unleash that and let them, let's say, have a more prominent role in the electricity market, it could have actually a lot of consequences. A final point related to that is the network charges. I mean, we know in Denmark, for instance, most of what we pay for when we buy electricity as a household is taxes and grid-related cost. 85% from this document of Eurelectric is not related to energy. And so actually, that's the point Henrik was making. We may also want to modulate this part to also support the way the various agents in the electric power system or integrated energy system would contribute. So that can be CO2 related, but my point here is that it may also be network related. So if we have agents that can exchange electricity, right? So it's in a market setup, it's not physically, but still we can reflect how each and every trade between agents will induce some stress on the network. So if 2 agents are neighbors and they just want to exchange some PV from a rooftop, the stress on the overall network is going to be quite minimal. So why should they pay the same network charges than agents that, for instance, are buying electricity from the other side of the country from an offshore wind farm? So we've been looking at how you can redesign network charges for accounting for the trades in a peer-to-peer system. And we've looked at many different alternatives. We can define an electric distance on the network based on different views. That can be PTDF, that can be TEVNA, that can be different views. So you would have directly the stress on the system. We can use a type of zoning, which is what we use also for public transport in Denmark, or we use also for different type of application. And all in all, with this work, we show that actually, depending on the way we redefine network charges, we will also incentivize people to behave in certain way in the way they buy or they exchange electric energy. So to conclude, a number of takeaway messages. First of all, this market-based approach for integrated energy system opens up to a lot of alternatives. There are many different ways we can look at how we can coordinate the system in a market-based environment. And obviously there's much more work necessary, both research and trying it out for real, that is necessary. What is key there is that the flexibility component in this integrated energy system comes from complex aspects to model and integrate in markets. So actually we need a new theory of market if we want to integrate these aspects optimally. So today, for instance, most markets are based on some linear programming approach mostly, and we propose to upgrade to some conic approach to do that. The uncertainty component is also very important, and we need to do more and more work in this direction. On the other side, the second part of my talk was about decentralization. And I think we need to invest more and understand better what would happen with these energy communities and peer-to-peer approach. And we should find ways somehow to make it work optimally with the current electricity market as it is today.
Pierre, thank you so much. Time is running.
Oh, sorry. I don't have the time. Yeah.
No, so I'll have to stop you here, and we'll have one quick question from Professor Henrik Madsen as we go into the break afterwards. So Henrik, can you please unmute yourself?
Yes, thanks, Pierre, for an excellent talk. Regarding your first topic, where you consider the coupling, loose coupling between electricity and heat markets. How did you take into account the flexibility or the dynamics of the district heating system? And how can you elaborate a little bit on how you did that?
Yes, but so there are different ways. That's what I was meaning with the complexity of doing it. There may be different ways to do it. You can look at the equations for the heat dynamics and the flow in the district heating, and you can try to linearize that, but then you realize it may not be enough. So then we looked at more advanced approaches. So the full models that we could consider, and then find ways somehow to bring that into some optimization machinery for the market. But yeah, eventually, as I was saying, if we really want to fully grasp the flexibility from the district heating side, unfortunately, it has a cost. We really need to model very thoroughly the dynamics in the district heating systems.
Yeah, because the district heating system is an excellent storage also of energy.
Exactly.
Yeah.
Exactly.
Thanks,
So there are different ways to do it, and there's always a balance somehow between the complexity in the modeling and optimization and what we'll get out of it in terms of how much flexibility have been grasped somehow.